Hey class, this is Mrs. Wendt, and we are going to be doing notes and some vocab work for Chapter 3. So in Notability, you have something, not Notability, but in Schoology, you have a file called Chapter 3 Textbook Worksheets. Please put that into Notability so you can fill in the answers together with me. Okay, after the video, I will give you some examples in the video, and after the video, you'll be able to solve the rest of them and hand the packet in. Okay, so the first page has some fill-in-the-blank notes. So I'm going to help you fill in the notes, and then I have some pictures to kind of help explain them for you as well. So you do not have to try to draw the pictures. You can if you want to, but they won't fit on your paper very easily. Okay, so the first part of our notes here, force and motion are connected. Okay, so what does that mean? Okay, well, if you remember, this word here, force is anytime you have a push or a pull on something. So you're pushing or pulling something to get it to move. Okay, so when you push or pull on something, there's probably going to be motion. So that's how those two guys are connected. Okay, now an object will have a greater acceleration, acceleration, will have a greater acceleration if a greater force is applied to it. So what that means is if you have more push, if you push on something harder, is going to be more movement. Okay, so the harder you push something, the faster it's going to get moving away from you. And then number 2, the other thing that kind of affects this is the mass of an object. Okay, so I have a picture down here to kind of help us with number 2. So this guy here is trying to pull a wagon. Okay, so to get the wagon to accelerate, you have to apply a force. So he has to pull it to get it to go from 0 meters per second to maybe, let's say 5 meters per second. Okay, so he's going to have to pull it to get that speed to change, which is acceleration. Now, if the wagon has more mass, so you can see there's more things in this wagon, he's going to need a bigger pull to get it to move. Okay? So mass is a big part of how much pushing or pulling we need and how fast that object's going to move. Okay? So Newton's second law of motion has an equation here. And it says acceleration, so how quickly something is changing its speed, equals net force, and we are going to divide it. Divided by mass, okay? So acceleration of something is going to be the force divided by the mass. Okay, so that's one way to kind of look at that. Okay, so the more mass you have, the more force you're going to need to get it to move. Okay, so here's another example here. Somebody playing ball. And you can see if they both swing exactly the same way, this baseball here that has a low mass is going to move much faster than this bowling ball that has a high mass. That one's not going to move very far, and then gravity quickly pulls it down to the ground. It doesn't have enough speed to keep going up. Gravity pulls it down. Okay. All right, so now letter C here. Another kind of force is something called friction. F-R-I-C-T-I-O-N. And friction is a force that opposes motion. Okay, and opposes means like opposite directions. Okay, so it's opposite between two surfaces that are touching each other. Okay, now I got a picture down here of this. So if we're trying to push the block this way, this rough surface, oh goodness, sorry guys, go back up there. This rough surface here has all kinds of places where the two blocks are going to kind of get stuck together. And that's going to be hard to get it to move with all those little rough, bumpy surfaces. So the rougher the surfaces, the more little bumps there are. And these little bumps have a special name. They're called micro welds. So micro for very small, and then welds, W-E-L-D-S. Okay, so that's areas where the surface bumps stick together, and they're the sources of friction. And lots of times you can't see these with your eyes. They're going to be really tiny, but these really tiny places will get stuck into the really tiny places of whatever's rubbing against it and cause this friction. Okay? Now, sometimes there's so much friction, things don't move. Okay, so like if you're trying to push a car that's broken, like a broken down car all by yourself, and you push really hard and it just won't move. It's too heavy. This is called static friction. S-T-A-T-I-C. Static means not moving. Okay, so sometimes there's so much friction that you by yourself can't get it to move. You might need some friends or a tow truck to get that car to move. Okay, the kind of friction you're probably most familiar with is called sliding friction. And this picture down here is sliding friction. Two surfaces sliding past each other, like these two boxes. This would also be your hands rubbing together. When, W-H-E-N, you are cold. So if you ever like been out at a football game and it's real cold out and you rub your hands together to heat them up, that heat you make is from the friction. So your two hands would be the two surfaces. They slide by each other, and that sliding friction creates some heat. Now, there's also friction between rolling objects, like things like tires, and that is called rolling friction. Okay, so a couple of these guys here. So picture A has a guy with skis going down a hill and a guy trying to slide down on grass. And I think that this guy over here is going to go faster because the smooth ice and the smooth skis are going to have less friction. Okay, now this guy over here, his rough bottom of his shoes and the rough grass, he's going to go a lot slower. In fact, he might not slide at all. He just might stand still with static friction. Okay, and because he has more friction between his feet and the grass than the skis and the snow had. Okay, I've skied once in my life. I'm not real good at it. But I have some friends that like to ski a lot, and I know at the bottom of the skis, they put layers of wax to make them as smooth as possible to make them go faster and faster down the hill. Okay, and then here's a picture of rolling friction. So if somebody's over here trying to push this ball, right here where the ball's hitting the ground, there's going to be some friction there. And depending on how heavy the ball is and how rough the ball is, how rough the ground is, that might be a lot of friction. All right. Now there's also friction in the air. So letter D here is air resistance. And resistance is R-E-S-I-S-T-A-N-C-E. Okay, air resistance opposes, so opposite directions, the motion of objects that move through the air. Okay, so I have a couple pictures here of a guy jumping out of an airplane. And when you fall out of the airplane, the force of gravity wants to pull you down. But there's all kinds of little air particles, tiny molecules of oxygen and nitrogen and carbon dioxide that are in the air. And they are rubbing against you as you fall. Okay? And the bigger you are, the more flat you make your body, the more air you have. Okay, so gravity is pulling this guy down, and the air is trying to slow him down, the air resistance. Now, after you pull a parachute, so over here, this parachute is going to catch a whole lot more of these air particles inside. And that's going to have a ton of friction with all those air particles. And that's going to make this guy gently float down to the ground. He's going to be going very slow because of all that friction. This guy here with no parachute, he's going to be falling really fast, and that could be a serious problem if he hits the ground. Okay? So the amount of air resistance that you have depends on your shape, right? So if you're falling out of a plane, do you make your body really small, or do you spread out your arms and legs to catch more air? Your size, do you have a big parachute or a little parachute to catch more air? And then also your speed. So jumping out of a plane, your speed's going to be caused by gravity. But if we think about things being thrown sideways, this is also going to be true for basketballs, baseballs, softballs, soccer balls going through the air. It's also going to be true for anything you're shooting, like a gun or an arrow or a Nerf dart. Birds and planes flying through the air. If you are into race cars, like NASCARs, sprint cars, Indy cars, cars are designed as they go down the road to have less air resistance. They have really smooth shapes, so it doesn't catch a lot of air. And that's why big semi-trucks that are shaped like a rectangle, they flip over on the highway because of the wind sometimes, more often than little cars will. Okay, now there is one more term here. Number 2. This is called terminal velocity. Terminal velocity. And the word terminal means end. So like if you are at an airplane terminal, that's the end of your flight. You get out of the airplane and you leave. All right, that's the end of the road. A ship terminal would be where the ship parks into port. Okay, so terminal velocity means your ending velocity. And that would be maybe this guy here in this picture. So let's say gravity is pulling him down with a force of, say, 1,000 newtons. But the air resistance is pushing up with that same force of 1,000 newtons. So those forces are balanced. Okay, they're the same and they're in opposite directions. And so he won't speed up anymore. He will keep falling with the same speed. So maybe he's falling down at 10 meters per second. So every second he goes down another 10 meters closer to the ground. Okay. So that's what terminal velocity is. And that's something that people can calculate. So people who are dropping things out of planes, whether they're bombs or parachute flyers, they can estimate when they're going to hit the ground and things like that. All right, now I want to show you this picture here. So here's a little boy, and he's got a ball and a feather. And if you drop them, notice that the ball is moving faster than the feather, because they both got dropped at the same time. And the reason is the feather has more air resistance. Okay, the feather is going to catch all kinds of little pieces of air here and help push it back up. The ball has a really smooth shape. It'll have a little bit of air, but not as much as the feather. Okay, it has nothing to do with their mass. It's all about their shape. All right, so we're going to switch gears a little bit. The reason those guys were falling was because of something called gravity. All right, so let's talk a little bit about gravity. Your book starts off talking about the law of gravitation. Same thing as gravity. Gravitation. Gravitation. Okay, and this says that any two masses exert a force on each other. Okay, so if you are standing on the playground and your friend is standing on the playground, you guys have a force pulling on each other called gravity. Okay, and everything in the universe has a force that's pulling on each other, and that force is going to be equal to each other and opposite of each other. Okay. Now, gravity is one of 4 basic forces that you'll learn about in college physics if you're interested. Okay. Electromagnetic force, that's kind of like positive and negative particles. And then there's a strong and a weak nuclear force that holds atoms together. Okay. So we are not going to worry about those forces in high school, but you may see them in college. Okay. But gravity, one thing that is cool, it works over a very long distance. So we call it a long range force. It gives the universe its structure. So gravity is what keeps the Earth going around the sun. Gravity keeps the Earth moving. Gravity keeps the moon going around the Earth. Gravity keeps all the stars and planets where they are at. So even though some of those things are millions and billions of miles away, we still have a gravitational force to them. So that's kind of cool. Okay. So I wanted to show you this picture here with the blue and the purple. So it says the force of gravity acts between all objects. And if the mass increases, the force of gravity increases too. So the bigger you are, the more gravity force you have. And if you go far apart, your force is going to decrease, right? And that makes sense. If you're far away from something, it's harder. It's harder to hold on to that. All right. So on this little planet Earth over here, this little boy and this little dog have a force. They're attracted to each other. And these two boys are attracted to each other by gravity. However, the biggest mass is planet Earth. So instead of the two boys falling towards each other and crashing into each other, they are all pulled down to the center of planet Earth because this Earth has the biggest mass out of anything around here. So that's the gravity force we notice. Whenever we drop something, it falls down to Earth because Earth has the strongest gravity force because it is by far the biggest thing we have. Okay, so this letter B here, due to the mass of things, Nope. What I'm thinking of comes later. So with this picture here, everything falls towards the biggest mass. Okay. Now, this word here in letter B is inertia. INERTIA. Don't worry too much about that. But everything falls. I want you to highlight this. Everything falls with the same acceleration regardless of mass. I grab my highlighter here. This is super important. Okay, if you drop two things from the top of a building or the top of a chair, they will fall with the same speed. There's a catch. Okay, remember this kid up here with the ball and the feather? They didn't fall the same because the feather had more air resistance. Air resistance is a force that messes this up. But if we took the air away, this ball and feather would in fact fall at the same speed. Okay, so check out this guy. Okay, so if we drop a hammer and a feather from like the top of a building, the hammer will hit the ground first because this feather has a lot more air resistance. It catches the air and just kind of gently floats down. This hammer has just this little hammer, a little bit of air resistance up here, but the feather's going to catch more air. However, if we are able to set up a vacuum, and a vacuum is a container with no air. The vacuum cleaners in your house, when you turn them on, all the air gets sucked out of the center, and that makes the outside air and dirt in your carpet get sucked into that space. Okay, so that's how a vacuum cleaner works. But just the word vacuum is any container with no air in it. They will fall at the same speed. And this was proved on the moon by the astronauts when they went up there in the 70s and they tried this experiment. So I wanted to show you the video of this. So let's see if this works with my screencast stuff here. And I'm hoping you'll be able to hear the sound.
And penetrometer drum in the ETB. Not quite yet. I haven't put the solar array in yet, but I will. I want to watch this. I have a good picture there. I've got beautiful picture, Dave. Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
All right. So that was real NASA footage from when they did this experiment. It's very cool. So hopefully the sound worked. If it didn't, he just kind of was talking to the camera about how he had a falcon feather because Falcon was the name of the spaceship they used as part of the mission. And then he had a hammer, and he talked about how Galileo was the first guy to kind of imagine this experiment. And Galileo was a scientist, and he actually dropped things off the top of the Leaning Tower of Pisa. And he dropped different things, and they all hit the ground at the same time, even though they had a different mass. So he was using kind of like bowling balls and cannonball kind of shapes. So they had the same air resistance, but they had a different mass. And they all landed at the same time. So he thought this would work on the moon, but we didn't have the technology to go to the moon and try it until several hundred years later. All right. So the next part here, kind of the top of the next page for you, we have a special word for the gravitational force that happens on an object. We call this weight. W-E-I-G-H-T. Okay, now when you take your weight, when you measure it on a scale, if you step on the scale, gravity is pulling you down to Earth. So it's a measure of how hard is gravity pulling you down on that scale. Okay, Now, if you were to take your scale and go on top of a mountain, you're farther away from the center of Earth, and your weight will actually decrease. Okay, so your weight decreases as you move away from Earth. If you take your weight in an airplane, you will weigh less than you would when you're standing on the surface. Okay, and that's because you're making the distance between you and the center of the Earth more. Okay, so weight is this force of gravity pulling you down. It is not the same as the word mass. Mass is a measure of how much matter an object contains. And matter is all of the atoms you're made of. Okay, so all the parts. So your mass is your head, your heart, your lungs, your stomach, your skin, your bones. That's all your mass. Your weight is how hard the force of gravity is pulling those parts down. Okay. Now, maybe you've seen some footage from a movie or from NASA things and stuff. But when you're in outer space, like in the space shuttle, there is no gravity. So you float around because there's no gravity to pull them back down. And things like trying to drink a cup of water, the water floats right out of the cup. Right, so everything has to be like in a little enclosed pouch, like a Capri Sun pack or a juice box, in order to drink things through a straw. Going to the bathroom is complicated because all of the waste will float around. So they actually have like little like vacuum cleaner tubes that they go into the bathroom in to suck the waste out. So the waste is not floating around. So a lot of things they had to invent because of this no gravity to make this work. All right. Now, let's say you're part of the Hunger Games book, and you're going to shoot, you have a bow and arrow here, and you're going to shoot an arrow. Okay. Now, when you let go of this arrow, you are making it so the arrow flies in a straight direction. But however, you also have gravity trying to pull this arrow down. And what happens is the arrow, when it leaves your hand, it's going to fly forward, but it immediately starts falling down due to gravity. And it's going to curve down until it hits the ground. Okay? These things that you throw forward, like an arrow or a bullet being shot out of a gun, or if you're throwing a baseball or a basketball, anything that is kind of thrown or shot forward has a name. It's called a projectile. Projectiles. Okay. Projectiles have a horizontal, so a sideways motion, and a vertical, like an up and down motion due to gravity. And they follow a curved path. Okay, so you should put these little arrows by the words horizontal and vertical to help you remember those. And so anything that's thrown forward is going to have this curved path because even though you're pushing it forward, gravity's trying to pull it down to the ground. So those two forces together will make it curve down. Okay, and then I got one more blank here. This last word, centrifugal, is a fancy word for circle. So some of the things that get pushed or pulled are going in a circle motion. And centrifugal force is what you feel if you're like on a roller coaster or a carnival ride where you're going in a circle. And you feel like you're getting pulled into the center of the circle. That's centrifugal force. Okay. So I have a couple of pictures here to kind of help with some of this. This first one here, if you're going to do some math problems later when you're going to calculate the weight and mass of things. But this is the math formula for that. So weight is whatever your mass is times gravity. And mass, we're going to always measure in kilograms. Gravity is measured in how fast it's pulling you down. So that's meters per second squared is the unit for gravity. And weight is going to be a unit called newtons. Any force, any push or pull is going to be a newton. And weight is a pulling down, so it's a newton, same as the other forces we talked about. And then this picture here just kind of shows a little example of how on every planet, everywhere you go, your mass stays the same. Okay? And the reason is mass is all of your parts together. So your head, your heart, your bones, your blood, none of those things change when you go from Earth to the moon. So your mass doesn't change because it's all the parts you're made out of. What does change is how hard gravity is pulling you down. Okay? The Earth is very big, so gravity is going to pull you down very strongly. So you have a pretty big weight. The moon is a lot smaller. It's got a smaller pull, so you're going to have a smaller weight. Space has no gravity. And 0 for no gravity, 0 times anything will be 0. So there is no weight in outer space. So your mass is constant. It does not change. But your weight is variable. It depends on where you're at and how hard gravity is pulling you. Now, most of us spend our entire life on planet Earth. So this doesn't really apply to us. Our weight stays the same because our gravity pull is always the same. All right. Last picture here, we have some centrifugal force here. So the guy in the center is pulling back on this ball, and this ball is trying to fly forward the opposite direction. But because it's on a string, it's going around in a circular path. And that circular path is really similar to what we have with planets and stuff. If we kind of pretend that this guy is the sun, and this little ball right here is Earth. Okay, this string is kind of like the gravity holding the sun and the Earth together, and the Earth is going around in an orbit path. So that's what centrifugal force is. It's just a force in a circle shape. All right, we just have a little bit left here, guys. Newton's third law of motion real quick. Newton's third law says for every action, we have an equal and opposite reaction. So OPPOSITE. Action-reaction forces, they're going to act on different objects. And I'll show you examples of that with the pictures. Okay. One of the best examples is rockets. So like rockets that go up into space is a really good example of Newton's third law of motion. And this law helped us figure out that the planet Neptune had to exist, even though we couldn't see it. Neptune is too far away for us to see without a powerful telescope, but we could tell that there was something really big out there pulling on stuff. We could see things being moved around because of the force. We just couldn't see the thing doing the pulling. So Neptune was predicted to be there. Astronomers started looking for it, and they did find it several years later. All right, so a couple examples here. So here is an action-reaction force. So the action on this balloon is when you blow it up and let go, the air is pushing out the back of the balloon. And the reaction, the balloon is going to go the opposite way. It's going to be pushed up. Okay? So the action is on the air moving. The reaction is the balloon moving. So it's two different things moving. and they're pushing each other apart. This cannon picture here, this is pretty common. If you watch like a pirate movie or a Civil War movie and you see them shooting off cannons, every time the cannon gets shot, the cannon will move back a little bit because of the force of the cannonball being shot forward. So this action of pushing the cannonball forward makes the cannon have a reaction going backwards. Now, because the cannonball weighs a lot less, this cannonball might go forward, say, 200 meters. Okay, because maybe this guy weighs 10 kilograms. All right, 200 times 10 would be 2,000. Okay, now this cannon here might weigh 200 kilograms. Okay, well, that means that the cannon would go backwards 10 meters. Now, that's probably too much. That's probably not a good example. It's probably better to say that this cannon weighs probably like 200 and I don't know. I can't do the math off the top of my head right now. But the cannon is probably only going to move, like 1 meter back. Whoops. Okay, so maybe the cannon then would weigh 2,000 kilograms. 2,000 times 1 would be 2,000. So they both equal 2,000. It's just divided a little differently between their mass and their distance. Okay, so basically, the bigger you are, the less you're going to move because of your high mass. And then in our notes, we said that a rocket is a really good example that a lot of times is used in textbooks. So when you shoot a rocket up, you heat up the fuel inside, and you explode the fuel. And that fuel flies out the back of the rocket at a tremendous speed. That's a huge force. Okay, so all the fuel is bursting out the bottom of the rocket. The opposite action is going to send the rocket up into the air. So this is the action, heating up the gas. The reaction is the rocket getting sent up in the opposite direction. Okay, so there's a couple examples. Your textbook has some more. Now we almost done, guys. I just have one more little tiny thing to show you here. 2 more blanks and 1 more picture. The last thing this book talks about is a word called momentum. Okay, momentum. And momentum is how much force you need to change something's motion. So how much pushing or pulling do you need to make it start moving, or to speed it up, or to slow it down? All of that could be used for a momentum. Okay. Now you can transfer momentum between one object and another, and we do not gain or lose any. That's called the law of conservation of momentum. Okay, and there's a formula for momentum here. Because the letter M is already being used for mass, somebody decided to use the letter P for momentum. I don't know if that was a great choice, but that's what it is. So momentum is mass times velocity. And remember, velocity is kind of another word for speed. So I kind of have a little train example here, guys. So we have a 30,000 kilogram train. And it's moving forward at 8 meters a second. And then it hits another train car. And they're going to go forward together then. Okay, so the momentum of this red car, the momentum would be our mass of 30,000 times 8. And then at the end over here, we have to have the same amount of momentum. We can't lose any. So the momentum on the other side is 60,000 of a mass, but times a number I don't know. Okay, now if you do all the math, what turns out is the number ends up being 4. So this car down here is moving at 4 meters per second. So we started at moving at 8, but now our mass is bigger. So we are moving at a smaller speed because it takes more to get that larger mass going. Okay, so that's just a real quick example of momentum. If you've ever seen, if you play billiards or pool, there's a lot of cool momentum things with that, where if you hit one ball, the other one will move slower or faster. Sometimes you can get a ball to stop and give all of its speed to the next one. That's momentum that you're switching from one place to another. Okay, there's some really good video clips on momentum in Schoology. So now what you guys have is you have some worksheets here where you're going to do a little bit of math and a little bit of vocab word here. But I thought it'd be useful to fill out these units real quick before we do this. Okay, so we're always going to measure mass in kilograms. Momentum is kind of a goofy unit. So we go back up here. Do you remember this where we took mass times velocity to get momentum? Well, mass is in kilograms and velocity is meters per second. So the unit for momentum is just those two things together. And the way I wrote it is how you're going to write it on your worksheet. So it looks a little weird, but that's what it is. Kilograms times meters per second. Distance, we're going to use M for meter. Force is the letter N, which is newtons, named after Isaac Newton. Time is seconds. Acceleration is meter per second squared. Velocity is meters per second. And weight is a force, so we use newtons for weight because it's just the force of gravity pulling you down. So it's got the same unit as any other force. All right, so this is going to help you identify numbers in problems and solve some problems. Okay, so our first problem here says, how much force, so here's our question, is needed to accelerate a 100 kilogram mass at a rate of 2.5 meters per second. Okay, so the first thing I'm going to do is kind of write down my parts here. So force is the thing I'm looking for. I have a 10 kilogram mass, so I know what a mass is. And meters per second squared. If I'm not sure what this is, I can go back up here. Like, oh, that's acceleration. So acceleration is 2.5 meters per second squared. So there's two formulas that I'm going to choose for all my math problems here. Force equals mass times acceleration to find out how much pushing or pulling I need. Or momentum, which is mass times velocity. Okay, so I have a mass and an acceleration and a force. So I think I need to use this top formula here. So I am going to show my work by writing my formula down. Force is mass times acceleration. And then I put my numbers in. I don't know my force, but I know my mass is 10 kilograms. And my acceleration is 2.5 meters per second squared. So 10 times 2.5 is going to give me 25. And if I'm not sure my unit, I can come double check. Forces are measured in newtons. So I will label that as a newton. And kind of put a box around there so the teacher can find my answer. All right. So for all these math problems, you have to choose which formula is going to be the one for the problem. Pick out the parts of the problem and write them down. Oops. Okay. So you have several problems to try. I'm not going